Welcome to another exciting adventure of Mr. Wernau Does Your Homework. Alright, so we're going to review series and sequences, and there's a worksheet that I have here for you. We're going to work a bunch of these, not necessarily in order. So it's 9.1 through 9.6 review. So it's everything from sequences all the way through the root and ratio test. We're going to see hopefully all of them a little bit today. So let's take a look at the first one right here. Now this is not a series, it's a sequence. So we just want to know if this converges or diverges. And these are pretty easy to do. It's very similar to the nth term test. So what we'll do is we'll take the limit as n goes to infinity. Now we know we should expand our factorial. So at the top we can expand the bigger one. And we get n plus 1, n, and then n minus 1 factorial. Once I get to the same as the smaller one, I can kind of stop. And on bottom I get this n minus 1 factorial. I can stop because those are just going to cancel. And if I let n go to infinity, of course this goes to infinity. Now infinity definitely does not converge. So we can say therefore the sequence, because this is not a series, diverges. And that's all you have to write. There's not really a test for this. It's just the sequence diverges. Remember, if it equals a number or a finite number, then it converges. Alright, so let's take a look at a couple of series then. Alright, for series number 3, now this is number 3 on that worksheet, so take a look here. Alright, so number 3 says we want to see if this series right here will converge or diverge, as n goes from 1 to infinity of 3n over 4n plus 1. This is just our nth term test, so if we take the limit as n goes to infinity, we get 3n over 4n plus 1, which is 3/4. This does not equal 0. So remember what this means. It's very similar to our sequences. This is saying at the very end, in other words, as n goes to infinity, we add 3/4 forever. That's what that is telling us. At the very end, as n goes to infinity, we're going to add 3/4 forever. So of course this will definitely diverge. If you add $0.75 to your bank book every day forever, eventually you're going to be very rich. So this will diverge by nth term test. So we can say the series diverges by the nth term test. Alright, number 5 is kind of a tricky one when you look at it, but if I were to rewrite this as n goes from 1 to infinity, n equals 1 to infinity, this is really just saying 1 over, that's n to the 1/3 times n to the first, or n to the 4/3. And now it's not so bad. This is just our p series. P is 4/3, which is greater than 1. And according to our p series, this will converge. So we will say the series converges by p series. Look at this, 3 minutes in, we've already done a bunch of these problems already, and you had to listen to my terrible analogies about adding $0.75 forever. These don't take too long. Now, number 7, of course you can pause this or slow this down at any given time that you like. For number 7, if we take a look here, this is not so bad. For number 7, you should recognize this, I think, alternating series. There's not too much work to do, but you should check it. Now you can do this check in your head. We just want to make sure that this series, that this term is heading to 0. Now, in nth term, we don't want it to be 0. But for alternating series, we do want this to be 0. So we would say our mantra. The series, ready, alternates, decreases in magnitude, and we just found the limit does equal 0. Therefore, the series converges by the alternating series test. Whew, that's a mouthful, right? But you want to write that down? You don't always have to show this step. You really just have to write your answer. It's the only one where there's not much work to do. Alright, here we go. Number 10. Alrighty. For number 10, we're going to use the integral test on this one. I think you can use a comparison, but we haven't seen the integral test in a while. So I'm going to use the integral test on this one. It's pretty ugly. So the first thing I'm going to do, I'm going to write my function in terms of x. That becomes 1 over x times the natural log of x squared right there. Pretty easy to do. So we will say the function f of x is positive, continuous, and it is decreasing in value, and decreasing. And you should say for all x is greater than or equal to 2. If you leave this part off, they're pretty okay with that, because that's our domain anyways, for all x greater than 2. So now what we do is we just take the integral. This is going to go from 2 to infinity, 1 over x, natural log of x squared dx. This is improper, which is why we don't like the integral test. So I got to rewrite this. The limit as b goes to infinity, 2 to b, 1 over x, natural log of x squared dx. Using u substitution, u is natural log of x, du is 1 over x dx, giving me dx is x du. Of course, these x's will cancel, and what we're left here is with u to the negative 2. So I'm going to write that up here so I can integrate that a little quicker. The limit as b goes to infinity. If I integrate u to the negative 2, that becomes negative 1 over u. Negative 1 over u, which is just natural log of x. So I'll go and plug that back in. And this becomes from 2 to b. Alright, so let's see here. The limit as b goes to infinity. We don't like the integral test. It's a lot of writing, but good practice for us. This becomes negative 1 over natural log of b plus 1 over natural log of 2. And now we're pretty much done. B goes to infinity. That's just 0. We're left with 1 over natural log of 2, which is finite and positive. So therefore we can say that because this is both finite and positive, this converges. So we can say that the integral converges. The integral converges because it's finite and positive. Therefore, the series converges as well. And that is by the integral test. Oh man, I don't know about you, but I'm going to take a break, come back for part 2, and we'll take a look at a few more examples. Okay, I'll see you then.